Building on our reflection of daily apps, let's dive into the core of how we define them. We start with functional requirements, or quite simply, the what. The core definition here is simple. These are the specific functions and services the system must provide. If the system doesn't do these things, it's essentially not fulfilling its purpose. To make this easier to grasp, let's use my favorite analogy, a restaurant. In a restaurant setting, functional requirements are straightforward actions. A customer must be able to order a meal, and the kitchen must receive that order. These are the basic tasks that make the business operate. Now, let's translate that logic back to the software reality we deal with as developers. In an app, this means a user must be able to reset their password or upload a profile picture. These are the explicit actions the system is built to perform. If you remember nothing else, just remember. Functional requirements are the must-dos. Now that we've covered the what with functional requirements, let's pivot to the how, the non-functional requirements, or NFRs. While functional requirements focus on the actions a system takes, NFRs define the system's performance and operational quality. Think of them as the constraints or standards the system must meet to be considered successful. Let's go back to our restaurant analogy. If the functional requirement is simply serving a burger, the non-functional requirement specifies that the burger must be served within 10 minutes. It's about the speed and quality of that service, not just the service itself. Similarly, we might say the kitchen must be able to handle 100 orders simultaneously. If the kitchen crashes when the 101st customer arrives, it has failed a key non-functional requirement. In the software world, we often call these the ILATs, because so many of the core categories end with those letters. These include scalability, how we handle growth; availability, how often the system is actually up and running; and of course, reliability and performance. Understanding these is crucial because a system that works but is painfully slow or frequently offline is essentially a failed system. Building directly on that thought, let's look at this comparison side by side to really solidify the differences between functional and non-functional requirements. Notice the categorization in this table. Functional requirements are your features and business logic, essentially the what of the system. Non-functional requirements are about quality and performance, the how well those features operate. Chloe, to use one of your grocery store analogies, the FR is the ability to find milk on the shelf, while the NFR is how quickly you can get through the checkout line. If the line is 3 hours long, it doesn't matter that the milk was there. This leads us to our core insight. It is a fundamental truth in architecture. A system that works but is painfully slow or unreliable will still fail in the real world because users simply won't use it. As Sam might note for his summaries, getting this balance right is the heart of professional system design. Now that we understand these requirements, let's see how we handle them as the user base grows. Next, we'll dive into the world of scalability. Building on what we just covered regarding system requirements, let's dive into one of the most critical concepts in modern architecture, scalability. In simple terms, scalability is the ability of a system to handle increased load. It's not just about staying online, it's about maintaining performance and reliability, even as the demands on the system grow. But what exactly do we mean by load? It depends on the context. It could mean more concurrent users visiting your site at the same time, a massive increase in the volume of data you're storing, or the number of database transactions per second. Think of it through the restaurant analogy. If you go from serving 10 customers a day to 10,000, your single kitchen and one chef will eventually fail. You need a strategy to scale your operations to meet that massive increase in demand. As we move forward, we'll look at the specific technical ways we can address this, either by making our existing chef faster or by hiring more chefs to work in parallel. Let's look at our first scaling strategy next. Continuing our look into scalability, the first approach we'll explore is vertical scalability, often simply called scaling up. Think of this as taking your existing server and making it more powerful. Instead of adding more machines, we focus on expanding the capacity of this one single server. In practice, this means upgrading the hardware. We might add more CPU cores for processing power, increase the RAM, or plug in larger storage drives. The main benefit here is simplicity. You generally don't need to change your application code or manage a complex network of machines. To use a kitchen analogy, imagine you're running a restaurant and orders are piling up. Scaling up is like buying a bigger, faster stove. It cooks more food at once, but it's still just one stove to manage in your kitchen. However, as seen in the visual, there's a catch. You will eventually hit a hard limit. There is only so much hardware you can physically pack into one machine before you reach the ceiling of what modern technology allows. Let's keep that limitation in mind as we look at the alternative. Instead of hitting that technical ceiling we just talked about with vertical scaling, we turn to the industry standard for big systems, horizontal scalability, or scaling out. The key concept here is simple. We add more machines to our resource pool. Rather than trying to build one super powerful computer, we use a fleet of standard machines working together. If you look at this diagram, you can see how the system expands sideways. This approach is what allows companies like Google or Netflix to handle millions of users simultaneously. Since you can always add another machine, there is practically no upper limit to your growth. To return to our restaurant, instead of searching for one world-class super chef who can do everything, we hire 5 more chefs and give each a small stove. It provides great reliability. If one chef is out sick, the other 4 still keep the kitchen running. However, as Chloe might have guessed, the catch is that it's much more complex to coordinate 5 people than just one. Keep this trade-off in mind, limitless growth versus coordination complexity, as we prepare for our next segment. Now that we've walked through the concepts of scaling up and scaling out, it's time to see them in action. In this simulation, you are the lead architect. Start by moving the traffic slider to the right and observe how our single server handles the incoming stream of colored dots. Notice that crash warning? As the traffic increases, the server starts to struggle. As we just covered on page 8, one option is to scale vertically. Click Upgrade CPU and watch how that single server begins to process those requests faster. Wait, even with a better CPU, we're still hitting a limit as we push the traffic even higher. This reminds me of Chloe's earlier grocery store analogy. Making the cashier faster only goes so far if there's still only one checkout lane. Let's try a different approach. Now, click Add Server to scale horizontally. This is the scale out method we explored on page 9. Notice how the dots are now distributed across multiple nodes. By sharing the load, we can handle much more traffic than a single machine ever could. Experiment with different combinations of upgrades and additional servers. Pay attention to how the system responds to heavy load when you have several smaller machines versus one giant one. You'll quickly see the flexibility that horizontal scaling provides. So, as we've seen, vertical scaling has a hard physical ceiling, while horizontal scaling allows for much broader growth. Keep these visual results in mind as we transition to our next topic, where we'll look at the wait times and volume of these requests.